All right, thank you. So hello, everyone. We are the North Carolina State University team, and we are given the Ohio State University use case. Next slide, please. For our team, we decided that it'd be best to split up the work to focus on the many different aspects that come with developing a PV plus storage system for Ohio State University. For our conceptual system design team, we have David and Helen. For financial analysis, we have Jacob and Gabe. On the distribution system impact, we have myself, Andrew, and Jennifer. And lastly, on the development plan, we have Madison and Jenna. All of us are sophomores in electrical engineering, while Helen is a senior in electrical engineering. Along with the help of our mentor, Ken, we also received assistance from professors and graduate students at North Carolina State University, as well as experts at Southern Energy Management and Energy Intelligence. Next slide, please. To implement PV at Ohio State University, we thought it'd be best to diversify the kind of PV systems we used. As seen here, we are using agrivoltaics at the pasture field nearby Ohio State University. Next slide, please. In addition to the agrivoltaics, we have both rooftop and carport PV systems to be implemented on select buildings on the Ohio State University medical campus, which range from hospitals to garages. Next slide, please. Next slide.
Our approach to designing our solar system can be summarized in 4 steps. First, determine the potential PV site within our given parcels. Second, select our equipment based on the type of solar panel due to site constraints. Third, determine our preliminary site layout based on research and talk to industry professionals. And lastly, optimizing our layout. Next slide, please. For the pasture land parcel, there are a number of obstacles we have to work around. For example, the field has trees sprinkled throughout the property, a pond located on the west side of the parcel, and 2 streams and fencing, which further divide the parcel into small subfields. Taking all these factors into consideration, we determined that the middle pasture, which is highlighted in yellow, would be the best location for our solar panels. Since there's already fencing, no new additional fencing would have to be placed, reducing the overall cost of the project. Next slide, please. For the medical campus, with the help of Aurora and Google Maps, we searched for buildings that were flat, had minimal obstructions, and were not shaded. All sites that were referenced with the Ohio State University Framework 2.0 document to ensure that there are no issues with the site we selected. Our final sites for the medical campus parcel are McCampbell's Hall, Dodd Hall, Telecommunication Network Center, Safe Auto Parking Garage, and 9th Avenue East and West Parking Garage, shown in yellow. Next slide, please. Our final site includes a mixture of buildings, park garages, and an open field. Naturally, our site constraints determine what type of PV systems we can place as well as the equipment we can use. For our buildings, we will be designing rooftop systems. For the parking garages, we will be designing carports, and for the field, we will be designing a ground mount system. Next slide, please. For our ground mount system, based on prior experience and speaking with industry professionals, we decided to go with a 2-up portrait single axis tracker with bifacial panels. After extensive research, we believe bifacial panels were the best choice for our agrivoltaic system. For inverters, we decided to use a central inverter as opposed to string inverters due to the size of the system as well as cost. For our tracker system, since we are using bifacial panels, it's important that our tracker is compatible with these types of panels. Additionally, we took into consideration the criteria of an agrivoltaic system and wanted a tracking system that would not be tampered with or in the way of grazing animals. Our final solar panels are from Lockheed, our central inverter is from CPS, and our tracking system is the Voyager tracker by FTC Solar. Next slide, please. Bifacials were also considered for rooftops as they sit upon concrete, and concrete has similar albedo values to grass. For carports, we decided to utilize monofacial panels. Because cars are going to be parked under the carports, having monofacial panels would help to keep the parked cars cooler. Our monofacial panels are from Canadian Solar, and our bifacial panels are the same bifacial panels we use in the field. For our rooftop and carport systems, we decided on using string inverters since our overall systems were much smaller. Something else we took into consideration when selecting our string inverters was that inverters had to have a rapid shutdown feature in accordance with the International Fire Code. Taking these criteria into consideration, we decided to go with the string inverter from SMA. Next slide, please. To model the pasture land, we first started by prepping the site in Aurora. Based on prior experience with ground mount solar panels, an offset of 20 feet was placed from the edge of the panels. And in accordance with the International Fire Code, a 10 feet offset was placed for all trees. Next, we modeled our preliminary site layout. Optimum string size for our design was determined based on our equipment. Spacing was initially determined using a ground cover ratio of 0.3. After the initial placement, we moved on to optimizing our layout design. Spacing between panels was decreased until shading presented in the panel and the row behind current panels when tilted on winter solstice. Our final ground cover ratio was 0.5. Next slide. To model buildings and carports, again, we started off by prepping the site in Aurora. For rooftops, an eave offset of 6 feet was set according to the International Fire Code, and all obstructions were given 3 feet setbacks. Like for the pasture land, we started by placing our initial site layout. Till and spacing was manipulated until we were able to produce max energy output with minimal shading. Our final layout for the rooftop panels were south-facing landscape panels tilted 15 degrees with a pitch of 16 inches. For the carports, some panels are not set up in rows like rooftop systems. That gave us the ability to tilt the panels a little bit more to more efficiently capture sunlight. After researching and testing the optimal angles, it was decided that carports covering north to south parking was tilted 30 degrees, while panels covering east to west parking was tilted 15 degrees. Once panels were placed, panels were then stringed together after determining the proper string size for equipment. Next slide, please. After determining our final layout design, the design information was transferred to SAM for the pastureland, McCampbell Hall, Dodd Hall, and Telecommunication Network Center. SAM is used for these sites as Aurora does not support bifacial modeling. For SAM, conservative values were used for albedo, shading, and equipment losses. Since our carports use monofacial panels, we modeled them in Aurora. Our final system size is 2,157,910 watts, and our annual production for all systems is 2,918,787 kilowatt hours. Next slide.
With regard to the distribution system, our system does not produce enough output to pose a generally high risk. Most of the output is significantly less than the given PV capacity at any given terminal on the campus. However, the potential overvoltage risks consist of where the panels are connected directly to the distribution system, such as at the field and parking garages, and downstream of height production. Per mentioned, nearly all of the PV output is well under the PV hosting capacity of the campus. And at very few times is the PV output ever greater than the total campus load. However, to mitigate any potential overvoltage conditions, we're connecting the PV directly to the loads where possible, such that panels on top of buildings will be connected directly to those buildings, producing minimal output to the grid. Furthermore, because batteries are not financially sustainable, as will be talked about in further slides, we will connect the PV output across loads. Assuming that OSU takes in 3-phase power, we can connect the parking garages and the field to different phases of that power to make sure there's always a load in between and thus always a voltage drop. Furthermore, smart inverters and sensors will be placed to clip the output if any overvoltage conditions are met in accordance to the utility standard at that area.
Thank you, Jennifer. Moving on to the financial analysis. Most of the return captured by investors is going to come from our PPA rate, which hovers around 10 cents per kilowatt hour for most of our systems. That does exceed the current rate that they're paying, but as we'll see later, some of the peak demand shading will offer this some returns for the customer savings as well. There's a 26% ITC that is involved in constructing solar PV systems, so there's additional return from that. And then there is also the accelerated cost recovery system, which has to do with offsetting depreciation of assets, which is also another way to offset costs. And then moving on to a little more of the customer analysis. So most of these savings that you see with that 33 cents per kilowatt hour comes from peak demand shaving. That's without a battery system. This is just taking into account PV because there's still times where peak demand coincides with peak generation from solar system. And then, as we mentioned before, the OSU special PPA at around 4 cents per kilowatt hour is difficult for us to beat, but we account for this later with Ohio State having their own independent energy goals, where they're putting green electrification as a higher priority than cost of the system, perhaps. And then looking more at the timeline for the investor benefits, due to the PPA rate escalation and the construction loan, a lot of the benefits are delayed towards the end of the life cycle of the project. Our break-even time was 13.5 years. This is specifically for the field. But overall, for the whole system, it's about a $5 million investment for a $2 million return over 20 years. And then, as we alluded to before, our ultimate recommendation was not to include an energy storage system alongside the PV. This mostly comes from cost. There was significant savings experienced through adding the battery system, but it couldn't be justified necessarily by our current model with using the Tesla megapacks in order to meet 40% of peak demand as required by the regulations of the competition. And then as you see, the demand curves or the price curves going forward, even with the low expectations, we'd still have to wait until about 2050 before lithium ion specifically reaches that $80 per kilowatt hour threshold that we're meeting with the savings. So ultimately, we would say our recommendation for Ohio State Medical Campus, if they were to include battery systems, would to be explore some other technology. And then the value of resilience is not necessarily captured here in that energy tool-based model. But one thing that we learned was that hospitals are required to have 96 hours of like basically fossil fuel with a generator in order to maintain that their critical circuits are working during an outage. And so that meant by adding batteries, we weren't necessarily adding any resilience to those critical care circuits. And so we found that you weren't really adding much resilience in terms of value by adding the systems. All you were doing is offsetting some fuel usage. But given the fact that there is roughly one outage per year at about 2 hours of duration, those are the SAIDI and CAIDI numbers for Ohio Power that we found that the building an entire battery system wouldn't necessarily offset those costs.
In regards to the development plan, we started by reviewing the university's Master Plan Framework 2.0. We chose buildings for rooftop solar arrays that were not specifically named as being replaced or set to undergo demolition, and selected locations that would not interfere with potential improvements for campus connectivity and transportation. More research went on to do included how animals interact with agrivoltaics. After researching how cows are not the best suited grazing animals for solar farms, we decided to introduce sheep in place of cows. We also checked floodplain maps to ensure flooding would not be an issue in our proposed locations, as well as considered glare regulations for the helipads in district and made sure there would be no intense glares coming from our arrays. Finally, we proposed a timeline for permitting, construction, and interconnection, and with the assumption that there would be no supply chain issues, our proposed timeline is 9 months. Next slide. We also know that getting the Ohio State University community on board with the project is essential to the success of its implementation. So we plan to involve the student population by engaging with student energy and climate organizations. For example, there is a student-led organization at OSU called Solar Education and Outreach, who aims to educate the community about green energy technology and initiatives. OSU also hosts Time for a Change Week, which is a collaboration between student organizations, campus administrators, and business partners to create a week with events focused on environmental awareness. This would be a great place to share and educate the campus about our project. We also want to specifically appeal to the agricultural department since the agrivoltaics will be on their pasture land. And as we educate the campus community about the plan, we want to foster excitement about helping their campus go green.
One of the driving factors in designing a PV system for Ohio State University was to help them achieve their district goals and challenges. Our PV system design will be able to help Ohio State reach its goal of achieving carbon neutrality by 2050. Along with this, the visibility of PV systems helps Ohio State University with its sustainability goal of outreach and engagement with both the on and off campus community. Lastly, using agrivoltaics instead of traditional PV helped to maintain livestock grazing on the fields. Next slide, please.
And as we approach our time, I would like to offer some specific considerations that put us maybe in a different category than the other presentations in the OSU use case. Some things we considered was specifically the agrivoltaic impacts on the livestock, which is why we recommended swapping out cows for sheep. We also wanted to make sure that we did implement the agrivoltaics because of the visibility of the system and how it creates a good picture for the green electrification of the campus. We also had those specific considerations with the hospital resiliency requirements, which significantly impacted our decision to not recommend energy storage. And then we also prioritized financial feasibility with those battery systems because we know that while they're pursuing green electrification, energy storage isn't necessarily part of that future. Then we also have a high diversity of design within our using rooftop, parking garages, and the agrivoltaic field. And then all of these different designs and not using energy storage made us be pretty creative with our distribution impact and how we needed to spread our loads based on the fact that we didn't have any energy storage to mitigate possible overvoltage conditions. And that is our presentation. Thank you so much for hearing us out. And we look forward to your questions.